You know that feeling, right? You hear about AI, then machine learning, deep learning pops up, large language models.
Oh, yeah.
It's just a lot of terms flying around.
Yeah.
And you're not quite sure how they all, fit together.
It's totally understandable. Things are moving so fast. It's hard to keep track, even if you're nearby technologically.
Exactly. So that's our mission today. We want to sort of cut through that. We're doing a deep dive using a really helpful structure from a Google AI course explanation we saw to give you a beginner-friendly look at these core ideas.
And clear roadmap, essentially.
Yeah, a roadmap. So you listening, if you want to get a solid grip on this stuff, quickly but, properly, that's what we're aiming for.
And the way this explanation starts is quite fundamental. It sets the stage immediately.
Okay, how so?
Well, it frames artificial intelligence, AI, not as one single thing, but as this really broad field, like physics.
Yeah. Okay, like a whole area of science.
Precisely. The big goal is creating machines that can exhibit intelligence. That's the umbrella.
Okay, AI is the whole universe then.
Yeah.
So where does machine learning come in?
Right, so machine learning, ML, is presented as a major subfield within AI.
A subfield.
Yeah, like if AI is physics, maybe ML is like thermodynamics, a specific branch, a way to do AI.
Got it. So under the AI umbrella, you've got this specific approach called machine learning. And then deep learning keeps coming up.
Exactly, and deep learning is then a further step down. It's a subset of machine learning.
Okay.
A specific technique within machine learning.
Right, it's like those Russian nesting dolls.
Yeah.
AI, then ML inside, then deep learning inside that.
That's a great way to visualize it.
So where do the LLMs, the large language models, fit? We hear so much about them.
They fit within deep learning as well, so that hierarchy holds. AI contains ML, which contains deep learning, and LLMs are a part of that deep learning picture.
Okay, that layered view really helps. AI, then ML, then DL, then LLMs. Makes sense. Now, the explanation we saw pointed at something specific. The intersection of generative models and LLMs. That's where things like ChatGPT and Bard come from.
Yes, exactly. That intersection is key. It's where the ability to not just analyze, but actually create new stuff comes from.
New stuff?
Yeah, the LLMs bring the language smarts, and the generative techniques let them produce new text, code, whatever. That combination is, well, driving a lot of what we see now.
Okay, high-level map established. Let's dig into machine learning itself then. What is it, simply put?
At its core, it's teaching computers to learn from data without explicit programming for every single task.
Right.
The idea is you use input data to train a model.
Right, you feed it info, it learns patterns. And
then that trained model can look at new data it hasn't seen before and make predictions or decisions based on what it learned.
it generalizes.
Exactly, it generalizes.
The video had that shoe sales example, Nike and Adidas. Can you walk through that again? You made it quite concrete.
Sure, so imagine Nike has like tons of historical sales data, styles, prices, marketing, customer info, everything. They use that data to train an ML model. Now, if they want to predict how well a new Adidas shoe might sell.
Even though it's Adidas, not Nike.
Right. If it has similar features, price point, marketing plan, they can feed that info into the Nike trained model. And it'll give a forecast based on the patterns learned from the Nike sales.
Wow, okay. Learning from one thing to predict another, that's powerful. Now, within ML, the explanation broke it down into two main types. Supervised and unsupervised learning. What's the basic difference there?
The key is the data they learn from. Supervised learning uses labeled data.
Labeled, meaning what?
Meaning each piece of input data in the training set comes with the correct answer or label.
Ah, so you're telling it the answer while it learns.
Pretty much. Think of the restaurant bill example. You have data on bills, amount, service, whatever, and for each one, you also have the tip amount. That tip amount is the label.
Okay, so the model sees the spill details and the tip it got.
Right, it learns the connection. Then, when you show it a new bill, without the tip yet,
It can predict the tip.
it predicts the likely tip based on the patterns it found in the labeled training data. It says, bills like this usually pay this kind of tip.
Makes sense. Supervised learning with answers. So what about unsupervised learning then? No labels. What's the point?
Well, with unsupervised, you give the model data without any labels and ask it to find structure on its own.
Find structure.
Yeah, like patterns, groupings. The employee example was good for this. You have data on tenure and income for employees, but no labels like good or bad, just the raw data.
Okay, just points on a graph, maybe. What can the model do?
It can look at that data and maybe find natural clusters, like Here's a group of people with long tenure but lower salaries. And here's another group, newer but higher paid.
Ah, it finds groups you didn't predefine.
Exactly.
Yeah.
It reveals underlying structures. Then you could ask, okay, this new employee, which group do they look most like?
That's useful for finding hidden insights. Now, there was a point about how they improve after making a prediction. A key difference.
Yes, a very important one. With supervised learning, after it makes a prediction on training data, it compares its prediction to the actual label, the known correct answer.
Okay.
The difference, the error, is then used to tweak the model, to adjust its internal workings to be more accurate next time.
It gets direct feedback.
Right. Unsupervised models don't have that. Since there are no correct labels to compare against, they can't adjust based on prediction error in the same way. Evaluation is more about the quality of the patterns found.
Okay, got it. Supervised learns from its mistakes directly. Let's shift to deep learning now. Explained as ML using artificial neural networks. Still sounds a bit techy.
Yeah. The core idea is using these networks with multiple layers. That's the deep part. They're inspired by the brain's structure.
Inspired by the brain.
Yeah, made of interconnected nodes or neurons arranged in layers.
So data flows through these layers.
Exactly. Each node does a small calculation, passes the result to the next layer. With many layers, the network can learn really complex patterns, kind of building understanding step by step.
More layers, more power generally.
Generally, yes. More capacity to learn complex relationships.
And the video mentions semi-supervised learning here. How does that fit with deep learning?
Right. Semi-supervised is often enabled by deep learning's power. It's a way to train using a mix of data, a little bit of labeled data, and a lot of unlabeled data.
So kind of getting the best of both.
Sort of, yeah. The small labeled set gives it some specific guidance, but the large unlabeled set helps it learn more general representations, making it more robust. The bank fraud example illustrated this.
Oh yeah, refresh us on that one.
Okay, so a bank has tons of transaction data. Labeling every transaction as fraud or not is, well, huge work.
Impractical.
Right. So with semi-supervised, maybe they label just 5%. They train a deep learning model on that 5% to get an initial idea of what fraud looks like.
Okay, starting point.
Then the model uses that initial learning to analyze the other 95%, the unlabeled data. It starts spotting patterns, flagging suspicious stuff, even if it wasn't in the original labeled set.
Ah, so it leverages the unlabeled bulk. Much
Yeah.
more scalable.
Exactly. Very useful in the real world.
Okay. Now within deep learning, the explanations split things into discriminative and generative models. What's the core job of each?
This is super important now with all the buzz around generative AI. Discriminative models fundamentally learn to tell things apart.
Tell things apart.
Yeah, classify data, answer, what is this? Is this email spam? Is this picture a cat or a dog? That's their main function. Learning the boundaries between categories.
Okay, they discriminate. Makes sense. And generative.
Generative models are different. They don't just classify. They learn the underlying patterns, the sort of essence of the training data, and then they can generate new data that looks like it came from that same distribution. They answer, how can I make something like this?
So instead of just saying, that's a dog, it could actually make a new dog picture.
Precisely. The video used the idea of training on lots of unlabeled animal pictures. The generative model learns animalness, ears, legs, fur patterns.
Right.
Then you prompt it, and it combines those learned features to create a totally new image of, say, a dog.
That is a huge difference. The video had a simple rule to tell them apart, based on output.
Yeah, a handy rule of thumb. If the model outputs a classification, a label, maybe a probability score, it's probably discriminative.
Like fraud or not fraud.
Exactly. But if the output is new content, text, an image, audio, maybe a 3D model, then you're likely looking at generative AI.
Okay, output type is the key, practical tip. So let's talk about those generative AI types the video covers. Seems like a hot area.
Absolutely. Innovation is crazy fast. First, text-to-text. That's your ChatGPT, your Google Bard. You give it text, it gives you new text back.
Right, most people have probably played with those.
Definitely. They've learned statistical patterns in language. Then there's text-to-image, Midjourney, Daily, Stable Diffusion.
The ones making pictures from descriptions.
Exactly. And importantly, many can also edit existing images based on text prompts, which is, powerful for creativity, but also raises complex issues.
Yeah.
Video mentions Google's image and video. Make a video. Still challenging to get right, but improving.
Video from text still feels a bit sci-fi.
It does. Then text to 3D. creating 3D objects or scenes from text. OpenAI's Shape-E was an example. Think game assets, virtual reality.
Just describing things into existence. Wild. Any others? The last one was text-to-task. Taking a text command and actually doing something. Like asking Bard to summarize your unread emails.
Translating language into action.
Basically, yeah, within a system.
Okay, that's a broad range of generative power. Let's zoom back in on large language models, LLMs. Where do they sit again?
Right, important recap. LLMs are a type of deep learning model. They overlap heavily with generative AI. Many text generators are LLMs, but they aren't exactly the same thing.
A key thing about LLMs is pre-training. They're trained on absolutely massive amounts of text and code first.
Pre-training. What does that give them?
It gives them a really broad, general understanding of language. Grammar, context, facts about the world, how words relate. It builds a strong language foundation.
What kind of general skills do they learn?
Things like classifying text, answering questions based on context, summarizing documents, predicting the next word, and generating text, which is key for the generative part. The video had that dog analogy for this.
Ah, yes, the dog. How did that explain pre-training?
Think of basic obedience training for a dog. Sit, stay, come.
Fundamentals.
Right. That makes the dog generally well-behaved, able to follow basic commands. That's like the LLM's pre-training. It gets good at the fundamentals of language.
Okay, general skills.
Yeah.
Makes the LLM versatile, but not specialized yet. So what comes next?
That's fine-tuning. After the broad pre-training, you can take that general model and train it further on a smaller, more specific data set.
Specific to a task or industry.
Exactly. You fine-tune it for a particular job, like the general dog becoming a
The
specialist.
police dog or the guide dog.
Precisely. So you could take a general LLM and fine-tune it on, say, legal documents to make it really good at legal tasks, or medical data for healthcare.
The video had that hospital example, right?
Yes, a great illustration. A hospital takes a pre-trained LLM, then fine-tunes it on its own medical records, research papers, doctor's notes.
All its specific knowledge.
Right. And that fine-tuned model can then potentially help doctors analyze images, summarize patient histories, maybe even suggest diagnoses, leveraging all that specialized medical training.
That really shows the power taking a general foundation and tailoring it.
Absolutely. It's a really smart model, as the video implied. Big companies build the expensive foundation models.
The pre-trained ones.
Yes. And then smaller organizations or specialized departments can take those and customize them with their own data for their specific needs. It's a kind of a win-win, accelerates progress everywhere.
So wrapping this all up then, we've gone through the layers. AI as the big field. Machine learning as a key approach within AI.
Right.
Deep learning as a powerful type of machine learning using neural nets.
Yep.
And large language models as sophisticated deep learning models, often pre-trained and then fine-tuned.
Got it.
And we've also seen the key difference between models that discriminate or classify and models that generate new content.
Exactly. And hopefully you, listening, now have a much clearer picture of how these pieces fit together.
Yeah, understanding these basics really helps make sense of all the AI news and tools popping up.
It empowers you to navigate it better, for sure. And maybe even use the tools more effectively.
Absolutely. So here's a final thought for you to chew on. Think about that pre-training and fine-tuning idea. How does that apply in your own field or maybe your own learning?
Ooh, interesting.
Yeah, what's the foundational knowledge? The pre-training everyone needs. And what's the specialized skill, the fine-tuning, that leads to real expertise? Mull that over. Might spark some interesting connections.